We had a speaker. Gary, the gift talk?
Yeah.
Okay, if you'd like that. And I went to the DICE conference, which is the Academy of Interactive Arts and Sciences conference. It is the best conference you can absolutely go to. If you ever get a chance to go or be a volunteer for this conference, go do it. And if you get to a game company and you can afford to go. The registration fees, I think, are about $2,000.
More than that.
But hotels in Vegas are really cheap. It's the Hard Rock Hotel. And it comes with all food paid and everything. And it's quite an exciting event. It ends with a big Academy Awards-like event, you know, showing what's the game of the year. And what was it? Last of Us won just about every award, as far as I could tell. And it was a very exciting time. We took one USC student, Khaled went, and he had a wonderful time. He got to meet, I think, about 50 or 60 game industry people. We also started out with a go-kart race. Go-kart race. In which, if you're interested, I think I posted my GoPro video onto Facebook. I was like, you know, so they did trials. I was the slowest person in the trials. It was about 50 or 60 guys.
Play more Mario Kart.
I know. I need to play more Mario Kart or something, or else I just need to go, you know, be a little bit more
People like show up to the track with bananas, like, I'm gonna win.
a little bit more reckless, you know. And then, you did individual trials, and you got rated, and then they took like a slow person and a fast person and put them on the same team, and then they took the next fastest, next slowest, and put them on the team, and they tried to even it out. So our team actually came in second place. And so the funny thing was that the second place prize was better than the first place.
So you meant to?
So the first place was you got a $150 spa treatment at the Hard Rock Hotel. And which is like, who had the time for that? But the second prize was $100 Amazon gift certificate. That's like, I can use that anytime, man. I live on Amazon. So we had a grand old time. And anyway, we have a guest speaker for you today. This is Hashem Alied. Is that how you say your last name?
Allied.
Allied. It's like Allied. Like Allied Band Company. Okay. He's going to talk on behavior-based approaches for detecting cheating in online games. He's a PhD student. This is the set of PowerPoint slides from his qualifying exam, which he gave like 2 weeks ago.
Yeah.
And he did great. And so I thought you guys might be interested in the way he thinks about detecting cheating, especially with respect to the online focus of this and the AI focus. So I'll let you. Okay, sorry.
I guess. So I'll be talking about my research on behavior-based approaches and detecting cheating in online games. First, we're going to talk about the motivation for this work. As you know, cheating in online games will give have many consequences, such as giving unfair advantages for cheaters over honest players, which will reduce enjoyment, and they will leave the game, and it will give a bad reputation for the game, and thus will lose money for the developers or the companies. There are many anti-cheating solutions available. Most of them focus on the client-side solutions, such as developing patches whenever cheat is discovered, or having programs to scan memory, which invades privacy, such as Funkbuster or the Warden of Warcraft. Some cheating examples we have, as you know, like aimbots and first-person shooter, trigger bots, wall hacks, in MMORPG, phishing bots and farming bots, and many other cheating examples. So in order to apply behavior-based solutions, we need to address these questions. So can we build an online game security system without the need to modify or with having minimum modification to the game? And that is actually by using the log traces only of the gameplay. What is the performance overhead of the system in terms of the gameplay and the network bandwidth? And what is the accuracy of the system? Also, can discover new cheats in the same category with fairly high accuracy? And finally, is the system centralized on the server or distributed? So we propose a behavior-based solution. This is a server-side solution with no interaction with the client. We will analyze players' data using two modeling techniques. As you can see here, cheat modeling and player modeling. So the cheat modeling part of the system We're going to use detailed player data to build a model for each type of cheat, and then we use classification. Finally, we use those built models for new unseen data to detect cheats of a similar type. In the player modeling part of the system, we're going to use detailed or aggregated player data, or even both, to build a model for each player this time. We're going to use clustering to cluster similar players based on their skill, and that depends actually on having enough data available. And finally, we're going to use anomaly detection to detect players using malicious behavior. The third part of the system, as you can see here, is called a decider. So the decider will take both percentages from the cheat modeling part and the player modeling part. We can combine both percentages. They will create an overall level of competence, which is based on a threshold. The threshold value depends on whether a player is an old player, a new player, the skill level, and many other criteria. The design of the system is going to be system generic, but we will use it on a first-person shooter game. The system will detect cheating behavior as well as any malicious behavior.
What do you mean by malicious behavior?
Malicious behavior, any like abnormal behavior, anything like that is not intended to be like
It's like an exploit as opposed to a third-party cheat or something.
yeah, any like cheating. Even like if it's abnormal behavior and then like you discover this is like he's using something legal, but like he's so now we're going to talk about like what has been done and what is missing. So we're going to talk about online game security in general, what is done in terms of non-behavior-based research and behavior-based research, and finally what is missing and what are the challenges for this work. So type of attackers, there are many reasons for cheating. Usually start with showing off their hacking skill, having fun, gaining attention, or even gaining glory in the game, or more dangerously like trying to steal money or compromising other computers. The common types of attacks, the most common one is bots, such as aimbot and trigger bot, and farming bots in RPG. Man-in-the-middle attacks, such as changing the death situation or obtaining more information in the world states in the MMORPG. Also, we have memory manipulation, collusion, which is rank boosting, trading virtual items for real money, which is illegal in most of the games. So what has been done in the non-behavior-based research? There are several papers published. Most of them focus on client-side solutions or even like a combination of client server-side solutions. One of them is a server-side bot detection will detect, it's focused on the movement of bots, like it's only focused on the positions of the characters. It will calculate the routes using waypoints. It's kind of simplified solution since it's only focused on the movement and the positions. Another one is enforcing semantic integrity. Try to detect invalid commands. They introduced the term semantic gap, which is the gap between the client concrete representation of the game and the server abstract representation of the game. They use an audit server. As you can notice, it will add an extra overhead for the client and the server. Server-side verification to detect invalid commands. The server will match legitimate execution of the client. This solution needs to modify the source code to allow symbolic execution. Another work is mobile guards to detect invalid commands and protect secret information exposure. So the server will force clients to download the mobile guards periodically. Those mobile guards are a segment of code that contains protection mechanism, and also to have like extra overhead. Ensure IT is a software by a company called Arxam. The solution needs to add guards on critical sections manually by the developers, and then they will add guards on top of the existing guards to have multiple layers of protection. They claim that their solution have a 2 to 5% performance overhead. FIDIS is a monitoring system. It's based on anomaly detection. So the client the server have a control that emulate the client, and the client have an auditor to accept control commands such as auditing data, memory, trace tags, and so on. For the behavior-based research, if you notice, our work is kind of similar to intrusion detection system. In the intrusion detection system, we have two main approaches: signature-based approach and anomaly detection approach. The signature-based approach, we need to store well-known attacks in a database and try to detect them. The drawback is, if you have a new attacks, it will go undetected. The anomaly detection, we teach the system on normal behavior of the users, and then it will detect any abnormality. The main drawback is false positives. So we're going to try to avoid that by teaching the system general behavior of cheats, and try to combine both cheating modeling and player modeling using the decider to get an overall percentage. So, what has been done in the cheat modeling part? A few papers were published actually. One of them talked about game bot detection using manifold learning. They focus also on moving bots. They used K-near snapper and support vector machines for classification, and isomap for dimensionality reduction. Another people, they used dynamic Bayesian networks to detect aimbots in a game called Cube. They used 5 features. They gained fair accuracy, however they needed to add more features. Other people used Unreal Tournament 3 SDK to build a FPS game. They used different bot types, different machine learning techniques. They gained high accuracy, but they had only 250 samples. Also, if you see the data, some features such as distance between the player and his enemy focused on having 2 players only. So it calculates the distance even if the enemy is not visible. So what if you have more than 2 enemies? In the player modeling part, actually almost no works, most of the works focused on analyzing player behavior in general or toward business modeling, but none toward cheat detection. One of the earliest works actually focused on analyzing human player movements to build a human-like AI agent based on human player behavior. Another people focused on clustering. They published several papers on different games, but they used only they cluster aggregated data for business model analysis. They clustered the overall aggregated data, so the overall accuracy of the player since he began until this point in time, the overall number of matches and so on. Other people try to have a dynamic difficulty adjustment by finding the just right difficulty using difficulty clusters. Also skill prediction toward better matchmaking. The skill was based on a questionnaire and mouse and keyboard inputs. So what is missing here? We need more research on bigger games. The player modeling, as you notice, player modeling research focuses on the business side. We need to utilize some work toward malicious behavior or cheat detection. The challenge is data collection. We need to collect a huge amount of data, and we need to manage this data. Also, the commercial game secrecy. Commercial game hardly share their data, and if they share the data, they don't usually they don't allow you to publish anything on the results of the data. Scalability of the system. It needs to be scalable and have contain more than 3 or 4 players. It need to handle a huge amount of players. So now we're going to talk about the parts of the system in details, the cheat modeling and the case study that we published, and the player modeling and our plan of doing that, and the decider also. So, in the cheat modeling part of the system, as we said, we build a model for each cheating and malicious behavior. So we're going to collect labeled data for both honest players and cheaters. And then we're gonna, for each cheat type, we're gonna build classification model using those label data. We're gonna have two phases, training phase and the application phase. So the training phase, we're gonna create a common built-in cheats first, and then collect both honest and cheating data records. We're gonna use the feature extractor to generate feature files, and then the data analyzer, we're gonna use those feature files to apply classifiers on them, and then generate models for each cheat type. In the application phase, we're gonna have new or unseen data, whether it's online or offline. We're gonna extract features in the same way we extract features in the training phase to generate feature files, and then we're gonna use our existing models that we built in the training phase to classify each record for each player, and then we're gonna produce for each player a number of cheating records. The decision is based on a threshold. The threshold is a number of flagged records. The value of the threshold depends on the accuracy of the system in the training phase, the policy of the detection, whether it's harsh or loose, and the detection time, whether it's online or offline. So our case study is a paper we published, me and Forrest, he's a TA here. So it's on a first-person shooter. The game contains the client-server architecture, and the feature extractor, and finally the data analyzer. So the game was developed here. The server responsible for communication and logging. We have two types of messages: event-based messages and heartbeat messages. The event-based messages for actions such as firing, spawning, and deaths, and so on. Heartbeat messages will have the player state, which will be sent periodically. The size of messages were small due to the bandwidth limitation. The client was developed using Unity 3D. We actually implemented the time-based death matches. The game is customizable. You can change the map, the duration, the protocol, TCP or UDP, the number of heartbeat messages per second, which will give you a good trade-off to check a good balance or good trade-off between the performance and the accuracy of the system.
What exactly do the heartbeat messages contain? I mean, you said the state of the player, right? So, I mean, what?
Yeah, like the position, the weapon used, the shooting, or
Okay.
yeah. So we applied the in-game aimbots, which are manually triggered on and off. The types implemented are lock, which is continuous, and instance, a simple aimbot. And then auto switch, which is a lock that will switch itself on and off automatically. Auto miss, which will create intentional misses. Slow aim, which is similar to lock, but it won't be instant. And finally, auto fire, which is simply a trigger bot. The feature extractor, in the feature extractor, we're going to extract useful features from the logs that will differentiate between an honest player and the cheater. They're based on time frames, so when we say time frames equal 30, that means every 30 seconds in the logs is going to be represented by one record in the feature file. If a feature is based on a target, it will be calculated only if the target is visible, and if we have multiple targets, we're going to choose the closest. We implemented 18 features. Actually, they're all, we talked about them in details in the paper. Data analyzer developed using Weka data mining tool. We use two classifiers, logistic regression and support vector machines using two kernel, linear kernel and RBF kernel. In the data analyzer, we train feature files to create detection models and then apply those models on unseen data. So for the experiments, we played 18 death matches. Each match is 10 to 15 minutes long. We had two human players in each match. So we collected a total of 460 minutes of data. The data transfer rate we chose were 15 messages per second. For the feature extractor, we applied the time frames 10, 30, 60, and 90. And for the data analyzer, we trained the classifiers using tenfold cross-validation. Also on the training phase, we organized our result in 4 different parts. The first one, we create one model for all cheats using multi-class classification. The second part, we combined the similar cheats together as one class, and we had like 3 class classification with one model. The third one is one model for a two-class classification, yes or no, or cheater, non-cheater. And the final one is having a model for each cheat separately. For the application phase, we played one death match, which is 30 minutes long. In this match, we had 3 players playing at the same time. One played normally, one used the lock cheat, and one used the auto-fire cheat. So the results for the multi-class classification part, the accuracy was almost 81%. The best classifier was logistic regression with frame size 60. If you notice here, the one in the gray, there was some confusion between lock-based, we call them lock-based cheats, which is lock, auto switch, auto miss, and slow aim. And auto-fire detected auto-fire accurately, and same thing with the normal gameplay. That's why we combined the lock-based cheats together in a two-class classification model, and we gained like 17% increase in the accuracy with SPM, RBF, and frame size 60. For the third part, when we combined all cheats together versus normal in one model, those are all the results as shown here. We noticed that we showed the true positive rate and false positive rate. The reason if the developers focus on detecting cheaters as harshly as possible, and that means that they might have a second level of detection, they should focus on a very high true positive rate, regardless to others. If they want to focus on non-detect, they don't want to detect like any normal player as a cheater. They should focus on the very low false positive rate, regardless to others. Like they might like let some cheaters go through. For the fourth part, which is each cheat classified separately or have its own model separately, the best accuracy achieved, the lowest was 98% for Ultimates, the highest was 100% for slow aim and auto-fire. Notice the frame rates are 60 and 90, so when you have higher frame rates, you can have less number of instances, and that might affect it like giving like a high number of accuracy. Also, like when you separate the cheats, separate models, you can have less number of cheat instances per model. So if we have more data, we might have like more reasonable results for this part. For the application phase, that's why for the application phase we used frame sizes 30 and 60 instead of using 90 and 60. And the classifier choosing the SPM with both linear and RBF kernels. So the results, the first table contains the first 3 parts results. Using the first 3 parts models, we applied them on the test data, and like we gained those results. So the first one is multi-class classification, the second one is two-class classification, and the third one is two-class classification. The second one is three-class classification. Sorry. The second table contains the results using models from part 4. Notice that we had 3 players, lock, auto-fire, and one was playing normally. So those are the models that we used and the results for each model. Notice that the lock-based models detected the lock cheat accurately, but they couldn't detect the auto-fire cheat. And on the other hand, the auto-fire model detected only the auto-fire cheat accurately. Also on the paper, we gave the top 5 features for each training part. The rank was given by calculating the square of weights assigned by SVM linear classifier. You'll notice that the ranking is different for different frame sizes, but the common top feature was mean aim accuracy, and for auto-fire, the top were fire-on-aim ratio and fire-on-visible ratio. We also gave some analysis and suggestions for developers who are going to use the same techniques for their game. First, they need full knowledge about their data. Also, if they face inaccuracy, some reasons could be, for example, delays or lag that will reduce accuracy of data collection. The cheating to normal data ratio should be between 50-50 and 40-60. They need to improve the feature set by adding new features or modifying existing features. Also, in online games, you're going to have a lot of unseen data. That's why you need to use a threshold, which is the number of cheating record per game per each player. So the threshold, once the threshold is reached, we flag the player as a cheater. the value of the threshold could be low, which is harsh, or high, which is loose. It depends on the detection accuracy of the model in the training phase. The developer's policy of detection, whether it's harsh or loose, and online versus offline detection. If it's online, should be quick and a bit loose. If it's offline, it could be slow and a little bit harsh. To apply the threshold, we get two different examples. For example, by using the part 3 model, which is the two-class classification, yes or no, with frame size 60, threshold 50%, and match within 30 minutes. First, you calculate what do you expect from each player, the number of records that you expect from each player. Actually, with lag, you're going to have less number of records, but like this is like, you should like fix a number so you can have a fixed threshold. And then multiply the threshold by the number of records. For the part 4, we're going to have the additional formula, since we noticed that the lock-based models detected the lock cheat accurately, and they couldn't detect the autofire cheat accurately. So we take the maximum of number of cheating records of lock-based cheats, and then add it to the number of cheating records from the autofire. To explain that, so we have like 5 different models. And we have 1 record for each player. So we apply it on this player. And for example, if each lock-based or each model give us like a number of cheating records for this player, we're gonna take the maximum of the lock-based models and then add it to the autofire model. And this is the total number of cheating records. And this is like, if we reach the threshold, we're gonna flag him as a cheater. So we finished talking about the cheat modeling part. What could be done here? As you notice, collecting more data for even different games. So if anyone also interested, like in having, if anyone have like an online game that is interested, like applying those techniques, you should contact me. Also, we need to conduct larger playtests over more distant networks. Using combination of multiple cheats in a single match, and finally building models for players instead of cheats, which is the basis of the second part of the system, and that is the player modeling, and we're going to talk about our plan of doing that. So the player modeling here is different from the cheat modeling. So we're going to build a model for each player or group of players instead of building a model for each cheat type. The data collected does not need to be labeled here, since we're going to assume it's a normal gameplay data. We're going to use different approaches, clustering and anomaly detection. The clustering will depend on the availability of enough data, since we need like a huge amount of data for applying clustering. For the data representation and the data modeling in this part of the system, so the data doesn't need to be detailed here. We could take a periodic aggregated snapshots. What do we mean here? Those are those snapshots will show us like the player progress during his whole play life. Such as in first-person shooter, we can take the match states, each match state as his snapshot. That contains, for example, kill death ratio, the favorite weapon, the accuracy for each weapon, and so on. For the data presentation, we're going to try, or we're going to use time series representation, which will be plotting skill versus time. And the skill will be a weighted average of those snapshot data. And also, we're going to try static representation, such as the actual snapshot data plus some other data, for example, the volume of gameplay for this player, the number of matches played so far, and so on. So we're going to use clustering to give us a good understanding of a player behavior in general, and it will help us with the anomaly detection process also. So we're going to have skill-based clusters, such as very skilled, poor, or average, poor, very poor. And the skill must be defined in the most useful way. For using time series presentation, we could use a k-means algorithm. But the problem here, we must equalize the length. We could have some other solutions, such as cutting snapshots from a certain time until now. For example, first-person shooter, we can have the matches from now and go back like 200 matches before, and if this is enough for representing a player behavior, we could have it as a fixed cutting time or window. Or we could use other techniques such as agglomerative hierarchical clustering using dynamic time warping as its distance measure, which will cluster time series even with unequal length. If we use the static data representation, we could use any other techniques such as k-means, EM clustering, and hierarchical clustering. For anomaly detection, we're going to have a semi-supervised learning here. So we're going to train on normal data only, or what we assume as a normal data, since we don't know like the player behavior in advance. The techniques are going to be used depending on the data representation selected. So for example, for time series representation, the one on the left, for example, a poorly skilled player who became like a very skilled player in a short time or no time. And this one, some companies like apply their cheat detection by changing the memory allocation every month they update. So the player will be, for example, a cheating player will have like a highly skilled at the beginning. This is his normal gameplay. He's highly skilled. So each monthly update, his cheat won't work anymore. So he will be like a poorly or average skilled player, and then like the cheat's going to work again, and then he's going to be a highly skilled again, and so on. That's what we expect to happen if we define the skill accuracy. So for anomaly detection, we have 4 different methods. We can use all or some of them, depend on the data we have and the time. So we have contextual anomaly detection for time series representation. Here we must define the context first. In first-person shooter, we could use the match number as our context, or the time. For example, using SACS, which is symbolic aggregate approximation. It's like a symbolic representation of time series, which will help with anomaly detection process. Clustering based anomaly detection for static representation. We could use we could try to detect outlier points that doesn't belong to any cluster, such as using DB-scan algorithm, or we can try to detect small clusters that will show us extreme cases in data, such as using archetypal analysis via SIVM. Third method, by trying to detect sudden jumps from a cluster to another, for example, from poor to excellent. And finally, using detailed data to build a model for each player. This time, we're going to build a model. So we're going to take the feature records for each player, and then build the model for this player, assuming this is his normal gameplay. And whenever we have a new record for each player, we're going to apply this model, such as using a multivariate Gaussian distribution. So we apply a PX, which is the model of the player, on the new record, and then it's going to give us a number. We're going to check it with epsilon. If it's less than epsilon, we're going to consider it as a cheating record. We also introduced levels of generalization. We can represent data as generalized, but it will be simple and might not be accurate. Or we can go detailed, which will be complex to implement, but it will be more accurate. For example, first-person shooter, we can have clusters for overall data of the player, or we can have clusters per each map, or even we can go in details and have clusters for each weapon, or even like for each weapon, for each map, and so on, or even for each kit in first-person shooter. So the challenges and limitations for this part. One of the biggest challenges is data collection. We need to collect a huge amount of data and manage this huge amount of data. Also handling new data, we could use online algorithms such as sequential k-means. Handling new items, if we use the concept of levels of generalizations, in the previous slide, whenever we have a new item, those clusters or those representation of our detection for each new weapon, and we don't need to change anything in the algorithm. The final and third part of the system is called the decider. So each modeling part of the system is going to give us a percentage, the cheat modeling percentage and the player modeling percentage. We're going to combine them into an overall percentage, which is a weighted average from each part. So the weight depends on the level of confidence for each part. So if both parts give us like a high accuracy in the training phase, we can have it 50-50 or in the middle like here. So and also like if it's an old player, we're gonna have enough data for playing modeling, and if it's a new player, we're not gonna have enough data for player modeling part of the system. So we're gonna have more emphasis on the cheat modeling part, and then it will reduce reduce gradually, like until like we reach the amount of enough data for this player. To evaluate this statement, we need to answer the questions we addressed in the beginning of this presentation. So building a model with a minimal modification of the game, as you can see from design, we won't modify the game. If there are any modification, it should be changing some simple changes in the messages exchange between the client and server and logging the data. For the performance overhead, we're going to compare the performance with and without the system. To evaluate accuracy, we're going to use different measurements, as you see in the case study. For discovering new cheats, we're going to implement new types of cheats and apply it on the system and see what is the detection accuracy. Or as you can see, we applied that in the case study also, like when we saw the autopilot on the log-based cheats. The system is centralized on the server, as you can see from the design also. This is the proposal plan of how am I going to do these things. So we're going to collect many data, hopefully in less than 4 months. And then demonstrating and evaluating the player modeling part by implementing that and generating results. And after that, I'm going to build and evaluate a decider. And finally, the dissertation writing hopefully will take like less than 2 months. As a conclusion, the problem here is try to detect cheats, detecting cheating without modifying the server or without invading the privacy of the client. So what has to be done and what is missing? As you noticed from the related work, a lot of work is missing toward the player modeling part of the system. So our solution is similar to an intrusion detection system where you have cheat modeling and player modeling parts, and then we're going to combine them as a hybrid system using the decider. That's all, and if you have any questions.
Yeah. So for a purely informational hack of the wall hack, you'd have to rely pretty much entirely on player modeling.
The wall hack actually, we can apply the cheat also, and store the. When you use cheat modeling, you're gonna implement a wall hack, and then play using the wall hack, and then you're gonna. This is how the player should be when he's using the wall hack. So when the system notices some similar behavior, he's gonna say, "Oh, this is a wall hack behavior." So you're gonna detect him as a wall hack cheater, for example.
And is that something that's done just through machine learning, or do you have more set? I'm just trying to imagine the kind of criteria you would have for that.
Yeah, you can use it in the machine learning. Using classifiers, and for the cheat modeling, you're going to use classifiers. For the player modeling, you can't use classifiers since you don't have. You're going to assume that this is only a normal data. You don't have any. This is a cheater. This is a normal player.
Other questions? All right, thank you.